Last time we were talking about non-covalent interactions and how they're connected to what you see in the world around you, and we had talked about the difference between soaps and detergents versus phospholipids. We had talked about how the conical shape of a soap, like a fatty acid with a polar head group and a single nonpolar tail, makes it so that when the molecule self-associates, it can bury the nonpolar portion, the nonpolar tail, inside a sphere. You line up enough of these individual cone shapes next to each other and you get a sphere or a micelle, which we talked about last time. In contrast, the cylindrical shape of the phospholipid with a polar head group and two nonpolar tails makes it so when you line up a lot of these phospholipids side by side, they don't curve as much. And so sequestering the nonpolar portion from water becomes more complicated. You can't just form a sphere. Side-by-side association of these cylindrical units leads to a monolayer that just has a nonpolar face and a polar face. But if you take two of those monolayers and stack them end to end with respect to each other so that the nonpolar stuff is inside, you then have a bilayer, which is what membranes are made of. The lipid that I showed you is important. This is phosphatidylcholine, and this is a zwitterionic head group. Notice that you have a negative charge on the phosphate group and a positive charge on this, what's called a quaternary ammonium. This is an ammonium that's bonded to 4 carbons, so there's no acid-base chemistry that can happen here to neutralize it. This is important because it means that on most eukaryotic cells, on average, there's not a really net positive or negative charge. That's important because that's not true for bacteria. So for bacterial membranes, the structure of the phospholipid is basically the same, except in the composition of that polar head group. So for bacteria, it's just called phosphatidylglycerol, and they lack the choline portion, excuse me, such that you just have the phosphate group, 2 negative charges. So what that tells you is then, and we'll use, let's see, what color have we used for negative charge before? Red. That tells you that a membrane composed of this kind of lipid should have a net negative charge. So we'll go ahead and make, tried, didn't we? We'll go ahead and use the magic of copy and paste to make a phospholipid bilayer really quick. Maybe not that quick. You get the idea. Oh, I should just, let's really go for it. All right, there it is. And then copy, paste, and flip. All right, there's our bacterial membrane. What you should notice if we contrast the bacterial membrane with the eukaryotic membrane is just that the bacterial membrane should be negatively charged, right? That's an important difference, and biology takes advantage of that as part of what's called your innate immune system. So your adaptive immune system has to do with B cells and T cells and antibody production, antibodies that are specific to particular pathogens in your body. But you have an innate immune system that's somewhat non-specific, but nonetheless can kill bacteria. A lot of organisms have this. And it's pretty important. And the way that it works is that you have a class of molecules that your body makes called antimicrobial peptides. So just keep in mind that the bacterial membrane is negatively charged, and then let's talk about briefly what I mean by antimicrobial peptide. We're not going to draw this molecule in all of its detail. A peptide is a short protein composed of amino acids. You'll learn about that more in 352. You've seen an example of a peptide in that horrible pKa versus pH problem that's in your practice exam. And I guarantee you there is a problem like that on your exam that's sitting waiting for you in the testing center. Nevertheless, a peptide can be divided conceptually into two different portions: a backbone, which is sort of a repeating unit that always stays the same, and then side chains, which can vary. There's 20 different side chains that nature uses in a peptide. A lot of antimicrobial peptides have a spiral structure called a helix, a spiral secondary structure. You may have heard about alpha helices and beta sheets before. Stay tuned for 352. You're going to get more of that, and also in biochemistry. But a lot of these antimicrobial peptides have what I'm going to call amphipathic character. That's the same word I used last time to talk about phospholipids and soap molecules. Amphipathic means both loving, meaning you've got a portion that interacts with water and a portion that doesn't prefer to interact with water, something that's polar and nonpolar in the same molecule. So these antimicrobial peptides, like soaps or detergents and like phospholipids, have amphipathic character. That is, they have one side that has a lot of nonpolar functional groups. I'm drawing just a few of these. It doesn't particularly matter what they look like. There are various amino acid side chains in nature that are nonpolar, and I'm drawing a few of them here. I'll just, maybe highlight these side chains in gray because that's the color we've been using in our drawings above for nonpolar functional groups. Now, I'm telling you that these antimicrobial peptides are designed to target the bacterial membrane, but of course it would be bad if they targeted your membrane. So you go ahead and tell me if I'm going to have one side of this antimicrobial peptide that's nonpolar, and I want my antimicrobial peptide to be attracted to the surface of a bacterial membrane, but not to your cell membranes, what kinds of polar functional groups am I going to want? Oppositely charged. If the bacterial membrane is negative, you want to have it be positive. So that's true. A lot of these peptides have side chains on them that are positively charged at physiological pH. You see why I care about that? Here's one of them. You will have seen this before. That's the horrible, scary ammonium one. This is the protonation state of an amine side chain that you have forgotten about many times until hopefully you remembered it and won't forget it anymore. But this is a positively charged side chain. And there are a few others, but we'll just draw the ammonium ones to remind you of that fact, all right? So if you have this peptide that is positively charged on one side, with positively charged side chains on one side, but nonpolar on the other, what can happen is that when that peptide gets in the vicinity of the bacterial membrane, the positive charges on the peptide associate with negative charges in the head groups of the membrane, and then there can be this flipping that allows the nonpolar portion of the peptide to embed itself in the membrane. Do you see how it sort of matches up? You got one side that's nonpolar, and so it should be able to interact with the nonpolar interior of the membrane, but on the surface it can interact with those positively charged head groups, ion-ion interactions. You get enough of these, and that starts to disrupt the bacterial membrane and even poke holes in the membrane. For example, you can imagine a situation kind of like this. I'm going to now, our drawing of that membrane is just, whatever. Sorry, I'm mourning the loss of what I'm going to do. So what I'm intending to, I need a bigger eraser at this point. Sorry. Egregious waste of class time in erasing. All right, so what can happen then if you get enough of these peptides close together in the membrane is that they can start to, copy, paste. They can start to coat the membrane and actually promote hole formation in the membrane. And why is that lethal to bacterial cells? Well, membranes are important because they make, the membrane is what distinguishes what's you from what's not you. It's especially important in bacteria. Shoot, I'm trying to talk and do stuff at the same time, which is always a challenge for me. Bacteria are packed full of DNA. They don't have chromosomes like you and me. The DNA is just jammed in. And once you poke a hole in the bacterial cell, the insides spew outward and the cell dies. So these peptides tend to make it possible to poke holes in the bacterial membrane and the bacteria basically explode. Okay? All of this, though, is based on things that you can understand now. The hydrophobic effect is a big one. The idea of positive charges being attracted to negative charges. And then the idea of molecules that are amphipathic, which means that they have double character. That is, they have a portion that's nonpolar and a portion that's polar. All right? Okay, so that's a couple more answers to what's going on there? I'm trying to just, there we go. All right. A couple more answers to our questions and things that are related to the world around us. Antimicrobial soaps sometimes have compounds like this. There are lots of antimicrobial compounds that have this same basic structure. Some of them aren't even based on peptides. Professor Savage in our department has a whole research program where he's invented a molecule that's really good at killing bacteria. He uses it to coat medical devices, endotracheal tubes, and it's having a really big impact. All right. So we've talked about membranes, we've talked about triglycerides, we've talked about why oil isn't soluble in water. I want to talk briefly about the difference between fats and oils. So I brought some peanut oil. This is several years old now. I've never opened it, but it probably isn't very good. But you can see that peanut oil is a liquid. Here's coconut oil. They call it oil because it comes from a plant, not from an animal. Nevertheless, this coconut oil is a solid, right? Whereas peanut oil is a liquid. Of course, I realized as I was going through my bag of oil and lipids this morning, I had butter in there that was several years old, which I promptly threw away because I didn't want you to have to smell it, I guess. But you can imagine what butter looks like. It's solid, right? Butter and oil, fats and oils share the same basic triglyceride structure. The real key difference between fats and oils, let's see, where are my triglycerides? Yeah. The real key difference between fats and oils is related to not only their source, oops, that's not the right one, where were we? There we are. Is related not particularly to their source. We tend to call things derived from animals fats, things derived from vegetables oils, or from plants oils. But in general, it's also related to the structure of the molecule. So I told you this was a triglyceride. And this type of molecule is what we're going to call saturated. The reason it is saturated is because all of the carbons in the nonpolar, what we're going to call fatty acid portion of the molecule, are fully saturated with hydrogens. There are no double bonds. Okay? You have heard of saturated fats. That's where this comes from. Just to keep you oriented, this portion of the triglyceride comes from the 3-carbon alcohol glycerol. And then this non-polar portion, which can be anywhere from like 10 to 18 to 20 carbons in length, we call that the fatty acid, because if you hydrolyze this ester linkage between glycerol and the non-polar portion, what would come off here is a carboxylic acid. And this is a saturated fatty acid. The saturated fatty acid would tend to be solid at room temperature. Now, you've heard the term unsaturated fatty acid before, so we want to talk about what that's like, and what that looks like. Let's see, if you'll give me a second, we can draw it. I'm going to repeat the glycerol portion of this molecule. I'm going to make our lives a little bit easier just by putting R groups there. I won't draw those two of the three fatty acids, but I will draw this one. This is going to be a monounsaturated fatty acid. It's 18 carbons long, so 1, 2, 3, 4, 5, 6, 7, 8, 9. On carbon 9, you have a cis double bond. So 9, 10, 11, 12, 13, 14, 15, 16, 17, 18. Okay? So there are some, this is a monounsaturated fatty acid. But there are other versions. For example, we could do the same 1, 2, 3, 4, 5, 6, 7, 8, 9. Another cis double bond. 10, 11, 12. Let's see, 9, 10, 11, 12. Another cis double bond. 13, 14, 15, 16, 17, 18. This is 18 carbons long with 2 double bonds. And then there's a version that would have 3 double bonds. So 1, 2, 3, 4, 5, 6, 7, 8, 9. Cis double bond 10, 11, 12. Cis double bond 13, 14. Let's see. And the last one is 9, 12, 13, 14, 15, 16, 17, 18. Okay? So this is, I think, 9Z, 12Z, 15Z. Why have I drawn all of these? Well, these are now sort of polyunsaturated fatty acids. In particular, the one on top is one that you hear at least used in marketing for various food products. Do you remember, I've probably used this terminology before, but in OChem we like to talk about how far other carbons are from key functional groups, and we'll just use Greek letters for that. So for example, we'll call this carbon the carbonyl carbon, and then this is the alpha carbon because it's 1 carbon away. And then we can sort of go from there down the Greek alphabet. If you spend a little bit of time in chemistry, you'll learn most of the letters in the Greek alphabet. At some point we stop counting. If you want to talk about if alpha is the one immediately adjacent to the key functional group, then omega is the one that's farthest away or at the end of the chain. So we call this end of the chain omega. And if you've ever heard the term an omega-3 fatty acid, that's what this is that I've drawn for you. See, notice that the double bond is 3 carbons away from the end. Okay? And so people will market that to you there, and I don't know any of the epidemiological studies about how the benefits of omega-3 fatty acids. This is, when you hear people talk about that, they're talking about triglycerides that have a large composition of this. I think the way they make your eggs rich in omega-3 fatty acids is they simply feed a lot of omega-3 fatty acids to the chickens. All right. So I will tell you that this triglycerides composed of a lot of unsaturated fatty acids. Unsaturated fatty acids tend to be liquids. Fats tend to be composed a lot of saturated fatty acids. Oils tend to be composed of a lot of unsaturated fatty acids. Okay? We should talk about why that is, but any questions before we go on about the general structure of triglycerides? Yeah?
When you number the carbons across, do you go through each Greek letter, or is it like alpha 1, alpha 2?
Do you go through each Greek letter? You can. So this would be the beta carbon, the gamma carbon, the delta carbon. of course, there's not, I forget how many letters there are in the Greek alphabet, and there may not be that many between the first carbon in this chain and the 18th carbon in the chain. It's more of a relative thing. Everybody knows if you say this is the omega carbon, you mean it's the one at the end. And so we sort of go from there. So on the other hand, yeah.
So the only thing that separates like saturated from unsaturated is like unsaturated have double bonds.
Right, the unsaturated have double bonds. Yep. You've probably been trained to think of the word saturated as evil and unsaturated as good, but actually has a technical definition, and it's just the presence of the double bond. Yeah. Is there a way to, sorry, I didn't hear that word, compress? Is there a way to write it down without drawing it out? Yes, there is sort of nomenclature. So if you read some of the food science literature, they'll tell you a C18 is a fatty acid with 18 chains, and then they'll tell you it has one double bond. Normally, biology puts that double bond in the same place. So if they tell you it's one double bond, you already sort of know that it's at the 9 position. Yeah. Or if it's 2 double bonds, you know that it's at 9 and 12. That has to do with biosynthesis, and I'm not exactly sure why, but that's how it works. Yeah?
Unsaturated is like all 3 of them together, monosaturated is one of them specifically.
That's right. Monounsaturated would be 1, and when it's mono, it's usually 9Z. Yeah. Yeah.
Are trans fats somewhat similar to either of these structures?
Ah, yes. Trans fats, are they somewhat similar? Yes, except you'd have the double bond, but it would be trans instead of cis. Yeah. We'll talk about in just a second where that comes from. What else? Yeah.
Does that pattern of having a double bond in saturated fats continue every 3 carbons?
Does that pattern continue every 3 carbons? I mean, it looks like it does if you compare 1 versus 2 versus 3. They're sort of, they're spaced apart by 1. Yeah. Okay, so let's talk about why the saturated fats are solid at room temperature, but why the unsaturated oils are liquid at room temperature. Now, we've already talked about van der Waals interactions or dispersion interactions and how these are related to how tightly related to the contact surface area between various molecules. So I'm going to copy something from the notes from a previous lecture. You've seen this, you've seen this before. You know that you get dispersion or van der Waals interactions between nonpolar groups, and that those interactions are extremely short range, and they only matter, they matter if the 2 molecules can get very close together, okay? And the more those 2 molecules can contact each other, the more extended surface area those 2 molecules have that can be close to each other, the stronger these van der Waals interactions are going to be. This will be our first time that we talk about something like melting point or boiling point. Basically, the stronger the intermolecular forces are, the more energy you have to put in to get molecules to move away from each other. And so that means the higher the temperature is going to be before something melts, all right? So let's, what I've drawn here is a pretty good zoom in of, what I copied here is a pretty good zoom in of the interactions between fatty acid chains within a triglyceride or between fatty acid chains on adjacent triglycerides. And these interactions are what you have to overcome when you want something that's solid to melt to become a liquid, or when you want something that's liquid to evaporate to become a vapor or gas. Let's now see the effect of putting a cis double bond in one of these chains. So let's see, we're just going to zoom in on the 9Z double bond in one of these unsaturated chains. Okay, there's one of them, and I'll use gray for the nonpolar surface area. The kink in that chain makes it so that the two molecules can't really approach each other as closely. Do you see how when the chain can be extended, you have sort of intimate interdigitation of CH bonds contacting each other closely? Because there's no rotation around pi bonds, this structure is pretty rigid, and the chains can't lay out next to each other quite as well. All right, I will write down, it may not be obvious from our drawing, but the presence of the double bonds results in smaller contact surface area, which results in weaker van der Waals interactions. I mean, still, these two molecules are still going to orient themselves such that, you know, the nonpolar face of one, they're going to have temporary induced dipoles where sorry, I'm distracted now by the way that this is, okay, yeah. Instantaneously, one face of the molecule is going to be partially positively charged, and the other face is going to be partially negatively charged. You're still going to get that, but it's not going to be as tight as for the fully saturated chain. Does that make sense? You've heard that before a little bit? Okay. So if that's true, then why is peanut oil a liquid, but coconut oil, which is also from a plant, is a solid? What's going on there? And to examine that, actually, you can study oils derived from various sources, and you can hydrolyze off the fatty acids and then analyze them to see what the composition is. And so I'm just going to write some data here for you so you can get a sense for things. Here we're going to write, let's see, saturated fatty acids, and over here we're going to write unsaturated fatty acids. And I'm just going to put the number of carbons in each fatty acid. It varies from 14 to, no, actually I want to include 12. 12, 14, 16, 18 carbons. And then for the unsaturated fatty acids, they're predominantly 18 carbons, either with the 9Z double bond or with the 9Z, 12Z, 2 double bonds. All right, and I'm just going to put the percentage of each of these fatty acids in different kinds of oil. And fat. So lard is animal fat. I served my mission 25 or so years ago in South Texas, little town called McAllen and Farr and San Benito in the Rio Grande Valley. There was this, maybe it's all over Texas, but there's this grocery store called HEB. Sound familiar to anybody? You've seen HEB? Yeah, this was totally new to me when I went there, but you could get 5-gallon buckets labeled manteca. And that's lard in Spanish, and that's actually how you make the really good tamales. So if you want good tamales, make sure you cook with lard. You can tell that someone's made good tamales with lard by the translucent napkins and plates that are left behind after the tamales sat on the plate. Anyway, lard, animal fat, it'll depend on the animal, but this is just sort of in general, is about 25% saturated 16 carbon fatty acid, about 15% 18 carbon fatty acid, still about 50% of the 18 carbon mono unsaturated, and about 6% of the poly unsaturated. That doesn't add up to 100, that's okay. There are other things there that I'm not putting there for detail. But apparently, having this composition of saturated fatty acids is enough for the molecule, for the lard to be a solid at room temperature. You can still spread it. I don't know if you ever want to spread lard on toast. Never tried it. I don't know that I recommend it, but maybe it's good. Olive oil here is a liquid, so let's look at that and see its composition. It's actually much lower in the saturated fatty acids. It's 80% of the monounsaturated, 7% of the two double bonds. Peanut oil, also a liquid, you would expect it to have similar composition, and it does, about 7%, 16 carbon, 5% 18. Peanut oil is actually a little bit richer in polyunsaturated fatty acids. Now let's talk about coconut oil, because as you can see, this is solid. It's not that solid. You can heat it up and it can become a liquid, but you certainly can't pour it in its current state. Coconut oil and palm oil both tend to have a lot more of these saturated fatty acids. So coconut oil is actually 49%, 12 carbon, which is different than all the other fatty acids or triglycerides we've looked at yet. None of them have had a lot of the 12 carbon. About 8% 14, 8% 16, 2% 18, only 6% mono and polyunsaturated fatty acids. So, I mean, this is why coconut oil is so is a solid room temperature. All right, we need to deal with trans fats, and we need to also deal with rancidity, and it's related. Okay, what is rancidity? Have you heard of that before? Okay, what's it like? What is when oil goes rancid? What does it smell like? Just sort of nasty. Yeah, I brought some tostadas. These are likely rancid by now. Let's see if there's a best if used by on there. I don't actually want to know. It's been a few years. I brought this as a visual aid because some years back my parents moved from Wisconsin to Utah, and so now we go over every other week for Sunday dinner. And I am 44 years old, but my mother still does not trust me to be responsible. And frankly, that's insulting to my wife. Because if I can't be responsible, she can. But in any case, we often get assignments to bring to Sunday dinner, and they are sort of little kid assignments, like, oh, could you please slice the lettuce? Yeah, Ma, I think we can handle that. You'd want us to do something? No, that's okay. Anyway, it's just, I love my mother. I really do. This is not intended to be critical. But anyway, and this story comes back to reflect poorly on me. So one time, my assignment, we were having tostadas. It was to bring the tostadas, all right? I didn't have to cook the chicken. I didn't have to slice the lettuce. I didn't have to prepare salsa or grate cheese. I had one job, and that was to bring the tostadas. Well, we had some. We don't use these very, very rapidly in our house, and we had some sitting in the pantry. I picked them up, and we went to Mom's house, and we started eating, and there was just this weird, you can sort of almost smell it, just like something is not right. It turns out the oil in the tostadas had gone rancid because they had sat in our pantry for too long, proving that my mother was right and I cannot be trusted to do the right job at the right time. Anyway, let's talk about what's going on with oil rancidity. Because this is a problem for oils, but not for fats in general. Not for fully saturated fatty acids. You have learned that, so let's zoom in on one of these double bonds. You've already learned that molecules with double bonds in them are more reactive, hydrocarbons with double bonds in them are more reactive than hydrocarbons without, because of the presence of the double bond. You've learned about the HOMO and the LUMO, right? The pi bond acting potentially as a nucleophile. Well, there's a whole other set of chemistry that can happen that you'll learn about a little bit later this semester called oxidation chemistry. And in the presence of an oxygen atmosphere, O is in brackets there just to indicate I don't exactly know what's doing the oxidation, but you can actually get removal of a hydrogen atom from the position that's adjacent to the double bond. That sounds bizarre. It'll make a little bit more sense at the end of the semester. There used to be two hydrogens there. Now there's only one, and in the place of the other one is a single unpaired electron. That is called a radical. The reason that can happen is because the radical is stabilized by resonance with the adjacent double bond. And over time, that radical can react with oxygen molecular oxygen in the air to make what's called a peroxide or an allylic peroxide, where you now make an oxygen carbon bond. And that does not taste or smell good. And there are other products, I think, that can come on after that. But basically, you damage, in the presence of oxygen, the carbons adjacent to the double bond oxidize, and then the triglyceride no longer tastes or smells good. All right? So that's rancidity, and this is why molecules this is why foods that are prepared in oil have limited shelf life, prepared with oil have limited shelf life, because this thing just sort of happens. Okay? Yeah?
But things in like peanut oil go rancid faster because it has more of the polyunsaturated fat.
Right, you would predict that things like olive oil and peanut oil should go rancid faster than coconut oil, which has far fewer double bonds. Exactly. So, and if you've served a mission and carried a thing of consecrated oil through some subtropical climate for 2 years in your pocket, and then after your mission somebody asks for a blessing and you open it up and it smells terrible, you need to throw that away and get yourself some fresh consecrated oil, because consecration does not prevent rancidity, right? Yeah.
First oxygen removes the hydrogen, and there's only one hydrogen left.
Right.
And then the O2 combines with that hydrogen to make the rancid smell.
Right. Yeah, and you don't need to worry about the details of this reaction, other than just the idea that the presence of the double bond allows this kind of thing to happen. So the food industry's smart, and years ago, I'm sorry, go ahead.
So if you seal an oil bag, would that open it at all? Or
Sure, if you keep it closed, if by the chance you carry around a tank of argon or nitrogen with you, and always after you open it up, spray the top of the oil with nitrogen to keep the oxygen out, yeah, that would help. Some of the preservatives that are used in the food industry are all about preventing this oxidation step from happening and intercepting the oxygen molecules. Right, so let's see. There was one more thing. Don't usually lose my train of thought in front of the class. That's kind of embarrassing. So the food industry is smart and knows how to avoid this, and they thought years ago, why don't we just get rid of the double bonds? And of course, plants are easier to grow than animals are and less expensive, so why don't we just isolate oil from various sources, and then we can convert it into saturated fats by chemistry, and then we don't have to worry about rancidity. And in some cases, maybe for various food products, you don't actually want oil, you want the fat to be more solid. So the solution there in chemistry is something called hydrogenation. You will learn about this reaction in, I think, Chapter 10. You take hydrogen gas and a transition metal catalyst, in this case, palladium metal immobilized on carbon or charcoal, and then you can add hydrogen across this double bond, reducing the saturated hydrocarbon to a fully unsaturated molecule. And this way, you now don't have to worry about rancidity. You've also gone from something that was liquid to something that's solid. The hydrogenated triglyceride, the hydrogenated oil, is more shelf stable. It's also a solid rather than a liquid. So you can look at your peanut butter next time you are eating peanut butter with the spoon. Maybe you don't, maybe you're just spread it on stuff. Maybe you're like me and you like to eat it with the spoon. In any case, while you're doing that, turn and look at the label and see. It may tell you that that has hydrogenated vegetable oil in it. All that means is they've converted at least some of the double bonds, reduced them down to the full alkane, and that's why the oil in your peanut butter is solid. If you have peanut butter that has not gone through that process, a lot of times you'll see a layer of oil on the top that you have to stir up. Have you ever seen that? You go to the grocery store, you see peanut butter in a weird little container and there's oil at the top, and you're like, who would buy that? the reason you would buy that is if, well, we'll explain that in a second, but the reason the oil is there is because that's not been hydrogenated. Okay? All right, so what's the issue with trans fats? Well, sometimes this hydrogenation process is kind of an equilibrium process, and sometimes it's not complete. Sometimes they only do it partially. You can read on food labels where they say this is partially hydrogenated whatever oil. And when that happens, at least some of the cis double bonds isomerize to form their trans isomers. And that's because, well, for reasons we'll talk about a little bit later, the trans double bond is more stable and less crowded in terms of atoms bumping into each other than the cis double bond is. In the cis double bond, you have these groups that are adjacent to the double bond that bump into each other. No such issues in the trans. And so oils that have been partially or incompletely hydrogenated sometimes have some amount of these trans fatty acids in them. And that's sort of the source. Now, in terms of the food science and epidemiology about the impact of trans fats, I don't really know a lot about that other than they are associated with negative cardiovascular outcomes. The big point is they're not actually supposed to be there. There are not that many natural sources of trans fats. Another observation is that because the trans double bond is locked into this extended shape, you actually get decent van der Waals interactions with trans double bonds, and so fatty acids with trans double bonds tend to be solid, where their corresponding cis double bond analogs would be liquids. Okay, well, that's a ton of stuff. I think I had intended to talk about GC versus AT base pairs. I don't know that that's useful at this point. It would simply be me drawing them and saying, behold, a hydrogen bond. And so I think we'll leave that perhaps for another time. All right, that concludes chapter 3. What I want to do now is give you an introduction to what's next. I don't think you care right now because you are worried about the exam. So because you don't care, we're going to look at some molecule simulations. And of course you don't need to draw all of this, but this is ethane. For this next section of the class, it may be good for you to learn how to use your molecular models, because what we're going to learn has a lot to do with three-dimensional shape. You will ultimately get so you maybe don't need the models to visualize in 3D what's going on in molecules, but until then you maybe should get yourself a model set. So this is the molecule ethane, 2 carbons, 2 CH2 groups. Notice I've told you before that the sigma bond between those 2 carbons, you can rotate around it. To show you that, I'm going to just grab onto one of these hydrogens and spin. And you can see that, let's see, I'd probably need to turn down this a little bit. You can see that we're free to spin sort of via propeller action around that bond. I want you to pay attention to what happens, though, when I spin around that bond, because you start to see, especially towards the end, something going on. If you notice what happens at the end, the sort of shape the molecule goes to, do you notice that the carbon-hydrogen bonds in the front are sort of in between the carbon-hydrogen bonds in the back? That's not a coincidence. That's the energetics of the system sort of make it be that way. Let's try that again. I'll just spin around. And you can see it's almost like spinning a wheel on the wheel of fortune, if you've ever seen that. Clunk, 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 chink, 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 chink. There you go. That's the energy minimum. So sound effects are optional. If you look at this molecule from this sideways perspective, it's sometimes difficult to see what's going on. If we look down, if we arrange ourselves so we're looking straight down the carbon-carbon bond, so the carbon in the back is immediately behind the carbon in the front, this view of the molecule is called a Newman projection. But you can see here that the energy minimum is to have the carbon-hydrogen bonds in the front interspersed or staggered with the carbon-hydrogen bonds in the back. We call this a staggered conformation, and it is an energy minimum. Notice that as I spin around the bond, it's passing through conformations where the CH bonds in the front are aligned up with the CH bonds in the back, but it's not staying that way. Let me turn up the temperature just a little bit. All right. I wish I could hold it constant and spin. This is where you're going to have to get a model set, but do you see as it's rotating, you do have to go through a conformation where the CH bonds in the front are lined up with the ones in the back. But you can tell the one where they're lined up is high in energy because it doesn't want to stay that way. It wants to relax to have it be in this staggered conformation. A couple of terms that might be useful to introduce is the concept of a dihedral angle. I'm going to slow down the bath again so I can keep things still. A dihedral angle is simply an angle between two vectors. That's a math definition. You don't have to worry about it. This is, if we look down the carbon bond in this Newman projection form, the dihedral angle is the angle between the CH bond in the front and a CH bond in the back. I have a laser pointer somewhere. Probably not. Realizing that I can't point to anything on the screen. There we go. Ooh, okay, yeah. Dihedral angle is between this carbon-hydrogen bond in the front and perhaps this one in the back. That angle, if you measured it, would be 60 degrees. And this dihedral angle is also 60 degrees. So these two, in contrast, the dihedral angle between this proton in the front and this one in the back is 180 degrees. We would say that this proton is anti to this proton, but it is gauche or adjacent to this proton. All right. So what you will see is that in organic molecules, staggered conformations are always energy minima. Going through the energy maximum is difficult, and that's related, and we need to talk about why that is. So there I go. Ooh, that's fun. I spun the one in the back. All right. So staggered is where the dihedral angles are all 0. Sorry. Back that up. Staggered is where all the dihedral angles between adjacent protons are 60. Eclipsed is where all the dihedral angles are 0. And you can see that the eclipsed conformation is the energy maximum. Okay? There are a couple reasons why that is. The easiest to understand is called electron-electron repulsion. The carbon-hydrogen bond in the front is repelled by carbon-hydrogen bonds in the back. When they line up with each other, the repulsion is strongest. We call that when the dihedral angles are all 60 degrees, the protons are all, CH bonds are all separated from each other as much as they can possibly be, and we call that, and that minimizes electron-electron repulsion. The idea that some conformations are not as favorable as others is really important in OChem, and it's especially as you consider about rotation around carbon-carbon bonds, we call this torsional strain. It is torsional strain that makes the staggered conformation more stable than the eclipsed conformation. All right, so this is ethane. I'll give you just a preview of a slightly more complicated molecule called butane. And here we're going to look down the carbon-carbon bond in the middle. And here you can see that the methyl group on one end is anti or opposite to the methyl group on the other end. And we'll talk about the various shapes that can happen. We may get out a model set next time to go through this in more detail. All right, that's enough for today. Good luck on the exam, and I will see you.